Hi there, my name is Sonnleitner, and my focus at voestalpine for nearly 20 years has been on electrical steel. I welcome you to my presentation of one of the most important applications of electrical steel strip in our world today, the electric motor. Electric motors can be very big or very small, and they are found everywhere, in computers, household appliances, and a wide variety of industrial and technological drives. By the way, there are more than 100 electric motors in your car alone, even if your car is not powered by an electric engine. Electric motors convert electricity into mechanical motion. Generators work the other way around. They convert motion into electricity. But how do they do that? Let's take a moment to talk about this, because all shapes, types and sizes of electric motors operate on the same principle. Even though it seems like magic, it really is simple magnetism, electromagnetism to be exact. You can learn more about magnetism in the voestalpine steel tutorial that is dedicated to the topic of magnetism. We know that magnetic poles of the same type repel each other and poles of a different type attract each other. This is the principle that sets motors in motion. The secret of the electric motor is the utilization of this attraction in an optimum arrangement of several magnetic fields to create continuous rotational movement. Let's take a closer look at an electric motor and its individual components. In addition to various electronic components and wiring, each motor has two essential parts called the stator and the rotor. The rotor is a moving component that transfers rotational energy through the drive shaft to the application that is being powered. The stator typically surrounds the rotor. It is stationary and does not have any moving parts. The crucial question is how we get the rotor to rotate. Both the rotor and stator must contain magnets that have been arranged according to a designated pattern. The deciding factor is that the direction of magnetization be reversible for some of these magnets. Otherwise, a state of equilibrium would quickly be established and nothing would rotate. Which kind of magnet is used to change and adjust the direction of magnetization? Correct. We need an electromagnet that uses an electric current to generate a magnetic field. To ensure that the electromagnet works properly, we must wind a wire into a coil around a core made of iron. More specifically, a core made of stacked laminations, made of electrical steel in the form of cold-rolled steel strip with special magnetic properties. Making the correct choice here is crucial because you can significantly increase the power and efficiency of your motor by using optimized electrical steel such as isovac made by voestalpine. High-quality electrical steel enables a lighter and smaller engine design without compromising power output. You can learn more about the important properties of electrical strip and how these properties can be adjusted in our steel tutorial about electrical steel. Now you can see why the rotors and stators of an electric motor consist of stacked laminations made of electrical steel in order to generate the required magnetic fields. Now I can create the desired magnetic fields by adding coils such as copper windings, or by placing permanent magnets in designated positions. The motor is then controlled by the electromagnets that make the rotor to rotate. Let's take a very simplified look at the basic design of an electric motor, beginning with the rotor. In our case, it is a simple permanent magnet in the form of a rod magnet with a central shaft around which it rotates. Additional magnets arranged around this rotor is called a stator. These magnets do not move, but the magnets in the stator can change their magnetic field, which is why they are called electromagnets. This is the same principle as in the coil winding. Deliberately reversing the polarity of the stator magnets with a continual change in the direction of the coil current changes the direction of the magnetic fields and generates movement. The attraction between permanent poles here in the rotor and the changing poles in our model in the stator leads to continual rotation. This principle can be reversed. The same setup is called a generator, when the moving part is driven by an external force such as wind or water to generate electric power in the windings. As I said earlier, my presentation is simple and cannot do justice to the countless types and versions of electric motors. Motors can generally be divided into two types: direct current and alternating current, or DC and AC motors for short. The main difference between AC and DC motors is the type of electric current that each motor converts into mechanical energy. And there is even more to it. DC and AC motors can again be divided into different types of motors. No matter whether motors are driven by alternating current or direct current, large or small, watt or megawatt, electric motors move our world, and all of them are based on the same operating principle. In order for motors to produce enough power and require the least possible amount of electricity, it is of crucial importance to use high-quality electrical steel, such as isovac made by voestalpine. Goodbye until the next steel tutorial.
Voestalpine, one step ahead.